This is the EdExcel A-Level Further Maths Paper 3 covering the Decision 1 module, and it's from the October 2020 series. Question number 1. The table below shows the lengths in kilometres of the roads in a network connecting 7 towns A, B, C, D, E, F and G. And that's what we see here. And for part A, by adding the arcs from vertex D along with their weights, we have to complete the drawing of the network on diagram 1 in the answer book. So if we go to the answer book here, we have diagram 1, and what we have to do in this question using the table here is complete this network by adding the arcs from vertex D over here. So for part A, we begin over here by looking at the row D and connecting this to A. You can see that has a length of 22 kilometers. So here we connect these 2 points and we add on the length 22. Then we have DB, that has a length of 27, so we can add this on. So here we have 27. Then we have DC, that has length 33, so let's add this. Here we have 33. We can't go from D to D directly. Now if we take a look at DE, the dash over here indicates we can't go from D to E directly. Let's take a look at DF. You can see that has a length of 42. So DF has length 42. Let's add this to the diagram. Here we have 42. And let's take a look at DG. There's no way of going from D to G directly. So this is the completed. For part B of the question, we have to use Kruskal's algorithm to find a minimum spanning tree for the network. You should list the arcs in the order that you consider them. In each case, state whether you are adding the arc to your minimum spanning tree. So, the way we will approach this is to, first of all, list the arcs in order from the smallest to the largest. So let's do that. So, by inspection, the order of the arcs is, so if we work through this problem, the smallest is AD. The weight here is 22. Then we have AB with weight 24. Then we have BC with weight 25. Then we have CG with weight 26. Then we have BD with weight 27. Then we have EG with weight 29. Then we have CE with weight 31. Then we have CD with weight 33. Then we have AE with weight 35. Then we have CF with weight 36. Then we have EF with weight 37. And finally, we have FG with weight 40. So now let's form our minimum spanning tree. We begin with AD. So we add on AD over here. And let's show we've accepted this by taking off AD. We then have AB. Let's tick it off. Then we have BC. Let's tick this off. Then we have CG, which is this over here. So let's tick this off. Then we have BD. We can't add BD because this would form a cycle, so we have to reject BD. Let's write down here, reject. Then we have EG. That's this over here. And let's tick it off. Then we have CE. This would form a cycle, so here we would have to reject CE. Then we have CD. This would form a cycle, so we'd have to reject CD. Then we have AE. We'd have to reject AE because this would form a cycle. Then we have CF. We can add this in over here. So let's tick this off. Then we have EF. This would form a cycle, so we'd have to reject EF. Then we have FG, which we'd have to reject, otherwise would form a cycle. So here we would have to reject FG, and therefore our minimum spanning tree is shown highlighted in yellow. For part C of the question, we have to state the weight of the minimum spanning tree. So to find the weight of the minimum spanning tree, we'd have to add together the different weights which we have accepted. So we have 22 plus 24 plus 25 plus 26 plus 29 plus the 36, and if we add all this together, it turns out we get 162 kilometers. Question number 2. The network in figure 1 shows the activities that need to be undertaken to complete a project. Each activity is represented by an arc, and the duration in hours of the corresponding activity is shown in brackets. For part A, we have to explain why each of the dummy activities is required. Well, first of all, you'd notice we have a dummy at the end of activity B. Now let's think about why we have a dummy at the end of activity B. You can see F and G depend on B. And you can see here H depends on C, but also H depends on B. So therefore, because H and G have a common activity, B, we require a dummy, as we see here. So let's put that into some sort of words. You can see then the dummy at the end of activity B is required, as activity F and activity G depend on activity B, but activity H is dependent on both activity B and activity C. Let's take a look at the other dummy we had at the end of activity K. You can see here we require a dummy because two activities cannot start at the same event and finish at the same event. In other words, we can't have an arc from here to here directly. We require a dummy. So let's write that down. So the dummy at the end of activity K is required as two activities cannot start at the same event and finish at the same event. For part B of the question, we have to complete the table in the answer book to show the immediately preceding activities for each activity. So in our answer book, we have this table over here. And let's just use this diagram over here. Of course, the only difference is the nodes are replaced with the early event time and the late event time boxes. This will just save us flicking between the pages. Now, if we take a look at activities A, B, and C, you can see those are connected to the source node, and therefore they depend on no other activities. We can indicate that using a dash. So we have a dash here, here, and here. Let's take a look at activity D. You can see D depends on A completing only. So here we write down A. Let's take a look at activity E. This depends on A completing only. So we have A over here. And if we take a look at F, this depends on B completing only. So we have B over here. If we take a look at G, this depends on B completing only. And if we take a look at H, Because we've got a dummy here, you can see h depends on b and c. So we write down b, comma, c. Let's take a look at I. You can see I depends on E and F. So we have E, comma, F. Let's take a look at J. You can see J depends on G and H. So we have G, comma, H. Let's take a look at K. You can see K depends on D and I completing. So here we have D and I. And if we take a look at L, this depends on D completing and I completing. So again here we have D and I. For the first part of Part C, we have to complete diagram 1 in the answer book to show the early event times and the late event times. So here we have diagram 1 for the first part of Part C, and we would have to complete this. Okay, so first of all, from the source node, we begin with the early event time, which is 0. Now, here we have 0 plus the 6, which is 6. Nothing else is going into here, so here we write down 6. Here we have 0 plus 7, which is 7. Nothing else is going in, so we write down the 7 here. Here we have to be careful. We have two options. We either have the 0 plus the 5, which is 5, or we have 7 plus the weight of the dummy, which is 0. So we've got 7 plus 0, which is 7, and what goes in to this box is 7. Before we figure out what goes here, we need to consider this box here, and that's because D is going into this box and I is going into this box. So, if we figure out what goes here, we have the option of 6 plus the 5, which is 11. So here we've got 6 plus 5, which is 11. Or we have 7 plus 3, which is 10. So 7 plus 3, that's 10. And we choose the 11 to go in here. Now, for this one, we have the 6 plus the 4, which is 10. Or we have 11 plus 4, which is 15. We choose the 15 to go in here. Let's figure out what goes here. We have the option of 7 plus 4, which is 11, or we have the option of 7 plus 3, which is 10. So we choose the 11 to go inside here. Here we have 15 plus 5, which is 20. So 20 goes inside here. And if we consider what goes inside here, we have the option of 20 plus the weight of the dummy here, which is 0. So we've got 20 plus 0, which is 20. Or we have 15 plus 6, which is 21. or we have 11 plus 6, which is 17. We choose the 21. So the minimum completion time you can see is 21, and for the late event time, because here we have the sync node, here we also have 21 for the late event time. And now we need to work backwards. So if we work backwards, here we have 21, take away the weight of the dummy, which is 0. Turns out here we get 21, so 21 goes here. If we work backwards to get to this point, we have the option of 21, take away 5, which is 16, or we've got 21, take away 6, which is 15. We choose the 15 to go here. Here we have 21 take away 6, which is 15, so 15 goes here. And here we have 15 take away 4, which is 11. 11 goes here. Let's continue to work backwards. Here we have 15 take away 3, which is 12. So 12 goes here. And here we have a couple of options. We either have 11 take away 3, which is 8, or we have 15 take away 4, which is 11, or we have 12 take away the weight of the dummy, which is 0. Turns out here we get 12. So here we write down the 8. And if we work backwards to get to this point, we either have the option of 15 take away 4, which is 11, or we have 11 take away 5, which is 6. So we choose the 6 to go here. And if we arrive at this point, of course, for the late event time from the source node, we want a 0. And this can be achieved by working backwards. So here we've got 6, take away 6, which is 0, or 8, take away 7, which is 1, or 12, take away 5, which is 7. So we choose the 0 to go here. Okay, so 0 goes here. For the second part of part C, we have to state the minimum completion time for the project. So if we take a look at diagram 1, you can see here the minimum completion time for the project is 21 hours. So the minimum completion time is 21 hours. And for the third part of part C, we have to state the critical activities. So if we go back to diagram 1, we're looking for the activities with 0 float. You can see A has 0 float, E has 0 float, I has 0 float, and L has 0 float. So for the critical activities, we have A, E, I, and L. For part D of the question, each activity requires one worker. Each worker is able to do any of the activities. Once an activity is started, it must be completed without interruption. And on grid 1 in the answer book, we have to draw a resource histogram to show the number of workers required at each time when each activity begins at its earliest possible start time. You can see here for part D, we have grid 1, and I recommend beginning with the critical activities. We have A, E, I, and L. And if we take a look at A to start off with, A has duration 6. So we have here A with duration 6. So that's filled in. Then we have E, and if we take a look at E, that has duration 5, and this takes us up to 11. So now we have E, which takes us up to 11. Then we have I, and if we take a look at I, that has duration 4, which takes us up to 15. So here we have I, and then if we take a look at L, this has duration 6, which takes us up to 21. So here we have L. Okay. So that's the critical activities shown. Let's now take a look at B. This has duration 7, and we start off at 0. So we have B over here. So let's just show this. It has a duration of 7. And if we take a look at C, it starts off at 0, has duration 5. So C goes here. Now, let's take a look at D. This starts at 6, and it has duration 4. So it starts at 6, so it starts here. It's got a duration of 4. But the problem is we can't have any gaps underneath like this. So here, let's just move these down to this point here. So here, we have D. E has been completed, so now let's take a look at F, which starts at 7 and has duration 3. So if we go back, F starts at 7 and has duration 3. Let's take a look at G, starts at 7, has duration 4. So G goes here, has duration 4, but because we can't have any gaps like this, this drops down here. If we take a look at H, starts at 7, has duration 3, so H goes here. I is critical, so that's already been added in. If we take a look at J, this starts at 11, has duration 6. So here we've got J. And if we take a look at K next, starts at 15, has duration 5. So 15 is over here, has duration 5. So k goes here. But because we can't have any gaps like this, those would drop down to here. Now let's take a look to complete this histogram by showing the complete box for the different activities. You can see here we have our completed resource histogram. For part A of the question, we have to determine whether or not the project can be completed in the minimum possible time using fewer workers than the number indicated by the resource histogram in D. You must justify your answer with reference to the resource histogram and the completed diagram 1. First of all, we saw in part D that 5 workers are required to complete the project within 21 hours, and that's shown here. And what we see as well, that between times 7 and 10 hours, currently 5 workers are required. Now, you can see here, activity A is critical, but activities D, F, G and H are non-critical activities. And we want to complete the project within 21 hours, but for us to do that, we want to use fewer workers than 5 workers. Let's see if we can use, say, 4 workers. Now, if I somehow start H at 10, then I would use 4 workers, but we have to see if this would affect the other activities and in turn affect the completion time. So let's go back to this diagram here. You can see the latest H can start is 12, and what we're saying is we want to start H at 10. So clearly this is allowed. So let's show this on the resource histogram. Let's show activity H on the resource histogram. So here, if we start H at 10, starts here, and we've got a duration of 3, but we have to see if this will affect any other activities, and clearly it does. Because J depends on H, we would also be delaying J as well, because J depends on H. So if we have activity H here, and it's got a duration of 3, what you can see here is activity H will complete at time 13. And because of this, we now have to delay activity J2. So let's just show J. So let's show this over here. And what we know already is J has a duration of 6, and we've delayed it by 2. Now, is this allowed? If we delay it by 2 and start it at 13, this is allowed because the late event time of J is 15. So we can start J over here, and it has a duration of 6. So this takes us up to here. Okay? So here is the amended activity J. And now what we have to do is determine the effect on k. Well, k is not affected by h or j, but over here we'd have to essentially move these activities up between 17 and 19. So let's just show k over here. This time, if we amend k, it's got a duration of 5, so I can still start over here, but because the duration is 5, this bit has essentially moved up, like so, because j is taking up the space, and this bit will still fall down here. So you can see, overall, with our amended histogram, we can still complete the project time within 21 hours. So let's just write all this down into some sort of words. So we can delay h to start at time 10 and start j at time 13. And that's because we can start h late as time 12 and j late as time 15. Question number 3. Direct roads between 5 villages A, B, C, D and E are shown in figure 2. The weight on each arc is the time in minutes it takes to travel along the corresponding road. The road from D to C is one way as indicated by the arrow on the corresponding arc, that's shown here. Floyd's algorithm is to be used to find the complete network of shortest times between the 5 villages. For part A, we have to set up initial time and route matrices. So if we go to our answer book over here, for the column headed by A for the initial route matrix, the entries will all be A, as we see here. For the column headed by B, the entries will be B. For the column headed by C, the entries are C. For the column headed by D, the entries are D. And for the column headed by E, the entries are all E. Let's take a look at filling the initial time matrix. We can't go from A to A directly, B to B directly, C to C directly, D to D directly, and E to E directly. So we fill these in with A dash. Let's take a look at going from A to B. You can see this is 8. A to C, that's 4. And if we take a look at AD, that's 7. And if we take a look at AE, because there's not one way which we can go from A to E, we show this with an infinity symbol. Now if we take a look at B to A, starting at B, finishing at A, that's 8. B to C, you'd find that to be 3. B to D, there's no one way of getting there, so we replace that with an infinity. And then BE, that's 10. Now if we take a look at CA, that's 4. if we take a look at CB, that's 3. If we take a look at CD, because there's no direct way of going from C to D, because the arc is directed from D to C, we replace that with an infinity. And if we take a look at CE, you'd find this to be 6. If we take a look at DA, this is 7. DB, there's no one way of getting there, so we replace this with infinity. DC, that's 1, because here we've got a directed network. And then DE, that's 1. If we take a look at EA, there's no one way of getting there, so we replace this with infinity. EB, this is 10. EC, this is 6. And ED, this is 1. So we write 1 over here. The matrices after 2 iterations of Floyd's algorithm are shown below. And for part B, we have to perform the next 2 iterations of Floyd's algorithm that follow from the tables above. You should show the time and root matrices after each iteration. So the key in this question is to realize that after the second iteration, we have these tables, and therefore when we were working out the second iteration, we considered the B column and the B row. So we can box those to show that we worked with these rows and columns during the second iteration, and therefore for the third iteration we will be working with the C column and the C row. And that's what we see shown here with the time matrix and the root matrix. Now, the entries along the diagonal of the time matrix will all be dashes, and along the diagonal for the root matrix we have A, B, C, D, and E. Now, the column C will remain the same as the previous iteration, so we have 4, 3, 1, 6. So let's show that. We've got 4, 3, 1, 6. The column C for the root matrix will remain the same from the previous iteration, which is all C's. So we have C's going down here. And for the row C for the time matrix, this will remain the same from the previous iteration, 4, 3, 11, 6. So here we've got 4, 3, 11, 6. And along here, we've got A, B, C, A, E. So we have A, B, C, A, E. Now, if we consider this element, we will compare the sum of 3 plus 4, which is 7, with 8. 7 is smaller than 8, so we change the 8 to a 7. And because we've changed this element here, we'll write down the entry C, because we're working with the column and row C. If we consider this element, we compare the sum of 4 plus 11, which is 15, with the 7 here. The 7 is smaller, so there's no change. So 7 goes here, and here we have D. There's no change. And if we consider what happens here, we compare the sum of 4 plus 6, which is 10, with the 18. You can see here 10 is smaller, so we change the 18 to a 10, and here we would have C. Let's consider this element. We compare the sum of 4 plus 3, which is 7, with the 8 over here. 7 is smaller, so we write down 7 here, and C here, indicating we've changed. For this element, we compare the 4 plus 11, which is 15, with what is here previously. So before, we've got the 15 here. So you can see here, the 14 is smaller, and here we write down C. And if we consider this element, we compare the 3 plus the 6, which is 9, with what we have here, which is 10. 9 is smaller, so we change to a 9, and here we have C. If we consider this element here, we compare 4 plus 1, which is 5, with the 7. 5 is smaller, so we put 5 over here and C here. For this element, we compare 3 plus 1, which is 4, with the 15 here. You can see 4 is smaller, and we change this to a C. And if we compare this element, we compare the 6 plus the 1, which is 7, with what's here previously, which is the 1. The 1 is smaller, there's no change, so here we've got 1, and the corresponding element here, you can see that was E. If we consider this, we compare the 4 plus 6, which is 10, with the 18. 10 is smaller, so we change to a 10, and here we write down the C. For this element, we compare the 3 plus the 6, which is 9, with what's here previously, which is 10, so we change this to a 9, and here we have a C. And here we compare 6 plus 11, which is 17, with the 1 over here. 1 is smaller, so there's no change. And here we have the D here, showing we have no change. Now with the fourth iteration, we'd have to consider the D column and the D row. So now we are considering the D column and the D row. So these elements remain the same. So here we've got 7, 14, 11, and 1. And here we have 5, 4, 1, and 1. And here we have C, 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 D, and E. And here we've got D, C, A, and D. Here we'd have the dashes, and here we have A, B, C, D, and E. Now for this element over here, we compare the 4 plus 7, which is 11, with the 7. There's no change, so we write the 7 here, and the corresponding letter remains as C. For this element, we compare the 1 plus 7, which is 8, with the 4 over here. 4 is smaller, so there's no change. So we write 4 here and C here. Now for this element, we compare the 7 plus the 1, which is 8, with the 10 here. You can see 8 is smaller, so we write 8 here, and here we change this C to D, as shown here. If we consider this element here, we compare the 5 plus 14, which is 19, with the 7 here. No change. So we write 7 here, and here the C remains the same. For this element, we compare 1 plus 14, which is 15, with the 3 here. No change. So here we have C. We now look at this element. We compare 14 plus 1, which is 15, with the 9. 9 is smaller, so there's no change. And here we have C. For this element, we compare the 5 plus 11, which is 16, with the 4. 4 smaller, so there's no change. So here we've got 4. And here we have A. If we take a look at this element, we compare 4 plus 11, which is 15, with the 3. 3 is smaller, so we have 3 here, and there's no change, so here we've got B. Now for this element, we compare 11 plus 1, which is 12, with the 6 over here. 6 is smaller, so there's no change, so we write 6 here, and E here. Let's now take a look at this element. We compare the 5 plus 1, which is 6, with the 10. There is a change, so we put 6 here and D here. If we take a look at this element, we have 4 plus 1, which is 5, compared with the 9. 5 is smaller, so 5 goes here and D goes here. We have changed. And we now compare the 1 plus 1, which is 2, with the 6 over here. 2 is smaller, so 2 goes here. And because we've changed, here we write down D. So this is the next 2 iterations complete for part B. The final time matrix after completion of Floyd's algorithm is shown below here. And for the first part of part C, we have to use the nearest neighbour algorithm starting at A to find a Hamiltonian cycle in the complete network of shortest times. Now the key is over here, because we are using a directed network, we have to read across the rows. So let's just write that down. So for a directed network, we have to read across the rows. Okay, so if we go back to our final time matrix, you can see here we were told that we have to start at A. So we label A with A1, and if we read across, the smallest entry in the row A is 4, so we circle it and delete A. So we delete A as we see here. So now you can see C is the next vertex. So what we have done so far is gone from A to C. That has a weight of 4. So we're at C. We read across for the smallest one. You'd find that to be B. So now we delete all of the C column, and we've just gone to B. That weight is 3. So now we're at B. So let's label B with a 3. If we read across, the smallest one is the 9 here. So that tells us we've gone to E, where is 9, and we now delete the B column as we see here. So now we're at E, so we label E with a number 4, and if we look across, the smallest one is 1. So now let's delete E, and you can see here we've just gone to D. The weight is 1. So let's label D with a number 5. And now let's delete D. And now that we're at D, because we need to find a Hamiltonian cycle, we have to go back to where we started, which is A. So to go from D to A, we'd have to add on this 5 shown in orange. So we have 5 over here. So let's just copy this into the answer book. So here we have our Hamiltonian cycle ACB EDA. And if we go back to the question paper, we have to find the time taken for this cycle. So for the next part, we add together 4, 3, 9, 1 and 5, you'd find here we get 22 minutes. And now for the third part, we have to interpret the cycle in terms of the actual villages visited. Well, if we go back to figure 2, let's just write down our cycle we have here. A, C, B, E, D, and A, and then here we had 4, 3, 9, 1, and 5. So A to C, that's 4, that's fine. And then from C to B, that's 3, that's fine. And then B to E, that's 9. So you can see to go from B to E, for a total of 9, we have to go via C. So we have to amend our cycle, so we have A, C, B, and then we have C here, and then E over here. So now that we're at E, we want to go to D, so that's 1, that's fine. And now that we're at D, we want to go to A, and that's 5. So we can't just go there directly, we have to go via C. So we have C here, and then we finish off with A. So this is the actual villages visited. So for the actual villages visited, we have A, C, B, C, E, D, C, and A. Question number 4. Figure 3 shows the constraints of a linear programming problem in X and Y, where R is the feasible region, and for part A we have to write down the inequalities that define R. Well, if we take a look at our equations, we've got 2y equals 5x, y equals x plus 1, and 6x plus 5y equals 30. What we can do to begin with is rearrange each of these equations so we've got y equals some function of x. Well, we can leave this equation alone, but we need to rearrange this equation and also this equation here. And if we do that, you'd find here we get y equals 5x over 2, and here we get y equals 30 minus 6x over 5. Now, the reason I want to do this is because this will allow me to find out which way the inequality signs should be facing. So, if we begin with the y equals 5x over 2, you can see here the region we don't want is everything above the line. So what this means is y will be less than or equal to 5x over 2. So if we write that down, you can see here y is less than or equal to 5x over 2. And if we take a look at this, you can see here the region we don't want is everything underneath the line. So this means that y is greater or equal to x plus 1. And if we take a look at what we have here, you can see we've got the region we don't want is everything above the line. So here we've got y being less than or equal to 30 minus 6x over 5. So now for part A, when we come to write down the inequalities, if we rearrange each of those, here we're going to have 2y being less than or equal to 5x. Here, no need to rearrange. We just have y being greater or equal to x plus 1. And here, if we rearrange this, you'd find we get 6x plus 5y being less than or equal to 30. For part B of the question, the object is to maximize p, where p equals 3x plus y. We have to obtain the exact value of p at each of the 3 vertices of R, and hence find the optimal vertex v. So before we do anything, we need to find the intersection coordinates and then substitute those coordinates into the objective function, and the largest one is where the optimal vertex will lie. So we can use our calculator to help us do this. So we need to solve some simultaneous equations. Now, if we go to our calculator, we have here simultaneous equations with 2 unknowns. So first of all, if we solve this line simultaneously with this line over here, then we are solving 2y equals 5x simultaneously with 6x plus 5y equals 30. So here we can type this in. We've got 5x minus 2y equals 0, and then we've got over here 6x plus 5y equals 30. So if we solve those simultaneously, you'd find we get 60 over 37 and 150 over 37. So let's just add that to our diagram. You can see here we've got 60 over 37, and we've also got 150 over 37. So that's this coordinate here. Next, let's solve this equation, the y equals x plus 1, simultaneously with this equation here. So if we go back, we are solving y equals x plus 1, so here we've got 1x and minus y equals minus 1. So if we solve those simultaneously, we get 25 over 11 and 36 over 11. So that means this coordinate here is 25 over 11 and also 36 over 11. And now if we find this coordinate here, we need to solve this equation simultaneously with this equation. So if we go back here, we've got 5x minus 2y equals 0 being solved simultaneously with 1x minus y equals minus 1. So here we get 2/3 and 5 over 3. So if we add that to our diagram, here we've got 2/3 and 5 over 3. So now what we need to do is substitute each of these coordinates into the objective function for p. Now we know already for part B that p is equal to 3x plus y. And we need to find out the value of p at each of these coordinates. So let's first of all find out the value of p at the coordinate 2/3 and 5/3. So if we substitute in the 2/3 and 5/3 in, we've got p equals 3 lots of 2/3 plus 5/3. So if we work this out, let's just go to the calculation matrix. Here we've got 3 lots of 2/3 plus 5/3. Turns out here we get 11/3, which is equivalent to 3.6, etc. If we now consider the coordinate shown here, the 60/37, and the 150/37, we've got p equals 3 lots of 60/37 plus 150/37. So if we work this out, just adjust this. Here we've got the 150/37, and here we've got 60/37. So here we get 330/37, which is equal to 8.9, etc. And if we consider the other coordinate, the 25/11 and 36/11, so if we consider the coordinate 25/11 and 36/11, we've got p equals 3 lots of 25/11 plus 36/11. And if we work this out, let's just change this. We've got here 25/11 plus 36/11, which is 111/11, which is equal to 10.0, etc. So here we've got the largest value for p, and therefore the optimal vertex is 25/11 and 36/11. For part C of the question, the objective is changed to maximize q, where q is equal to 3x plus ay. Given that a is a constant and the optimal vertex is still v, we have to find the range of possible values of a. Well, if the optimal vertex is still here, that means when we substitute this into q, substituting this coordinate into q will give a larger value than substituting this into q and this into q. So, for part C of the question, we begin with q equaling 3x plus ay, and if we substitute in the 25 over 11 and 36 over 11, we would have 3 lots of 25 over 11 plus a lots of 36 over 11, and substituting that coordinate in will give a larger value than substituting in this coordinate or this coordinate. So this will be greater than 3 lots of 2/3 plus a lots of 5 over 3. So if we work out this inequality, we have 75 over 11 plus 36 over 11 lots of a being greater than 2 plus 5 over 3 a. And if we rearrange, we have 53 over 33 lots of a being greater than minus 53 over 11, and therefore you'd find a to be greater than minus 3. And if we substitute in the other coordinate we have 3 lots of 25 over 11 plus a lots of 36 over 11 being greater than 3 lots of 60 over 37 plus a lots of 150 over 37. So we have 75 over 11 plus 36 over 11 lots of a being greater than 180 over 37 plus 150 over 37 lots of a. So we have minus 318 over 407 lots of a being greater than 795 over 407, and therefore, rather here we have a minus, so therefore a is less than 5 over 2. Question number 5. The 9 distinct numbers in the following list are to be packed into bins of size 50. So we've got the list of numbers as shown here, and you'll notice here we've got the number x. When the first fit bin packing algorithm is applied to the numbers in the list, it results in the following allocation. So for bin 1 we've got 23, 17 and 8. Bin 2 we've got 19, x and 10, and for bin 3 we've got 24 and 18, and for bin 4 we've got 21. And for part A we have to explain why x is in between 13 and 21. So The best way to approach this problem is to simply pack the bins in the order that we see them. So, for part A, we've got 4 bins. So, we can see that over here, we've got our 4 bins, and here we've got the allocation, and here we'll leave this column for the space left over. So we begin with the 23. Now of course, bin 1 currently has space 50 in it, as do all the rest of the bins. So if we take this 23, we place it into bin 1, and let's just cross it off. Therefore the space left over will be 27. Then we've got the 17. Well, there's enough space in bin 1, so we can place 17 into bin 1, and therefore the space left over will be 10. Let's just cross this out. Then we've got the 19. Well, there's not enough space in bin 1, so we have to place it into bin 2. So 19 goes here, and the space left over then will be 31. So let's cross off the 19. Now we've got this x, and if we go back to the question, you'd see x is placed into bin 2. So x goes here. So what does this mean so far? Well, the space left over then, that will be 31 minus x. So let's cross this out. Now if we take a look at the 24, 24 goes into bin 3. So we place 24 over here, and therefore the space left over here will be 26. Now why is this important? Well, what this tells us is that because we don't have enough space in bin 2, we had to place it in a new bin. So that tells us that 31 minus x is less than 24, because if this value 31 minus x was greater than 24, we could put 24 into bin 2, but we can't do that. So this will imply that x is greater than 7. Let's continue. So we've used up this 24. If we take the 8, well, 8 we can place into bin 1, and therefore the space left over will be 2. If we take a look at the 18, if we go back to the statement here, you can see 18 has been put into bin 3. So if we place 18 into bin 3, 18 goes here, and there's a space of 8 left over. But because 18 has been placed into bin 3, that tells us that there's not enough space to put 18 into bin 2. So that tells us 31 minus x is less than 18. And therefore, x is greater than 13. Now, if we cross this off and deal with the 10, well, there's not enough space in bin 1, and if we take a look at where 10 was placed, that was placed into bin 2. So that tells us that there is enough space in bin 2 to put 10 in, which means that (31 minus x) is greater than 10. And Therefore, you'd find x to be less than 21. So that's the 10 dealt with, and finally 21 is placed into bin number 4, leaving a space of 29. So from these two statements, we can of course conclude that x is in between 13 and 21 as required. For part B of the question, the same list of numbers is to be sorted into descending order. A bubble sort starting at the left-hand end of the list is to be used to obtain the sorted list. After the first complete pass, the list is as what we see here, and we have to use this information to write down the smallest interval that must contain x, giving the answer as an inequality. So here we've got our original list, and let's complete the first pass and write down the inequalities as we see them. So first of all, we compare 23 with the 17. Do they need swapping? No, they don't. So 23 can stay where it is. And now we will compare 17 with 19. Do they need swapping? Yes, they do. So 19 goes here, and 17 goes here. We now compare the 17 with the x. Now we need to think, do they need swapping? Well, if we go back to the list as we see here, no, they don't. So 17 stays where it is. Okay, so 17 goes here, and this means 17 is greater than x. Let's just write that down. So far, we've got x which is less than 17, otherwise x would have gone here. So now we've got this x, and we're going to compare it with the 24. Now, do they need swapping? Well, of course they need swapping, because 24 is greater than x, and we can figure out that out from this inequality here. Of course, because x is in between 13 and 21, that means that 24 is definitely greater than x. So we've got x which is less than 24. So 24 goes here, and x is over here. We then compare the x with the 8. Do they need swapping? Well, no they don't, because x will obviously be greater than 8 because x is in between 13 and 21. So x goes here, and the 8 goes here. And what we've just found here then is that x is greater than 8. So now if we finish off this pass, we compare 8 with 18. Do they need swapping? Yes, they do. 18 goes here, and 8 goes here. We then compare the 8 and the 10. Do they need swapping? Yes, they do. So 10 goes here, and 8 goes here. We then compare the 8 and the 21. Do they need swapping? Yes, they do. 21 goes here, and 8 goes here. So if we were to narrow down our inequality, of course, we can conclude here x is definitely greater than 13, but it will be less than 17. So here we have a smaller interval. For part C of the question, when the first fit decreasing bin packing algorithm is applied to the 9 distinct numbers, it results in the following allocation, and that's what we see here. And given that only one of the bins is full and that x is an integer, we have to calculate the value of x. You must give a reason for your answer. Well, we're given that only one of the bins is full, and clearly bin 2 is the only full bin. Of course, we've got the space of 50, and 21 plus 19 plus 10 is 50, so this is the only full bin. Now, you'd find over here, before x is placed into bin 3, the remaining space left in bin 3 is 15. And that's because 50 take away 18 take away 17 is 15. So let's just write that down. So the space before x is placed in bin 3 is 50 minus the sum of 18 plus 17, which is 15. So that means that if x is placed into bin 15, that means that x will be less than or equal to 15. Okay? So we can refine our inequality even further to say that x is greater than 13 but less than or equal to 15. So either x is equal to 14 or x is equal to 15. But we know bin 2 is full. So, but bin 2 is full, and therefore x cannot equal 15. Otherwise, if we place it into bin 3, rather they should say, but bin 2 is only full bin. So therefore, x cannot equal 15. Because if we placed it into bin 3, that means bin 3 will have 0 space left over. So therefore, the only solution we can have is x equals 14. Question number 6. For part A, we have to state with justification whether the graph in figure 4 that's shown here is Eulerian, semi-Eulerian, or neither. Well, first of all, let's find out the orders of each of the nodes. Here, we've got 3. Here, we've got 2. Here, we've got 4. Here, we've got 2. Here, we've got 4. Here, we've got 3. And here, we've got 6. And what you'd find is only A and G have odd order, and therefore we can conclude the graph has exactly 2 odd nodes, and therefore the graph is semi-Eulerian. For part B, the weights on the arcs in figure 4 represent distances. The weight on arc EF is x, that's shown here, where x is in between 12 and 26, and the weight on arc DG, that's y, where y is in between 0 and 10. An inspection route of minimum length that traverses each arc at least once is found. The inspection route starts and finishes at A and has a length of 409. It is also given that the length of the shortest route from F to G via A is 140. Using appropriate algorithms, we have to find the value of x and the value of y. So if we take a look at the diagram as shown here. Starting at A, we add in the working value of 0. The order of the labeling here is 1 because the final value is 0. Now, we've got 0 plus 24, which is 24. 0 plus 42, that's 42. And then we've got 0 plus 65, which is 65. So now the smallest one, that's 24. So B has a order of labeling 2 because the working value, the final value is 24. Now 24 plus 15, that's 39. And the smallest value from 39 and 65, that would be 39. So C has a order of labeling 3 because the final value is 39. Now we have over here 39 plus 21, that is 60. Then we have 39 plus 19, that's 58. We've got 39 plus 45, that's 84. And then we've got 39 plus 31, that's 70. The smallest of all of these is the 58. So A has order of labeling 4 because the current final value is 58. So here we would have 58 plus x. And now we need to find the smallest value from 58 plus x, the 70 and the 60. Well, we know already that x is in between 12 and 26, so the smallest value x can take is 13. So if we add 13 to 58, it turns out here we would get 71. So the minimum value we can have in this working values box is 71. So let's just write that down. So the current minimum working value here is 71 because x is in between 12 and 26. So smallest value x can take is 13, i.e. 58 plus the 13 is 71. So having said that, the smallest one is 60. So we have D with order of labeling 5 because its current working final value is 60. So now 60 plus 34, well, that will be 94. We don't want to add that, that will just give a bigger value here. So 60 plus y is the one that goes here. So now what we need to do is decide which value is smaller, the 60 plus y or the 58 plus x. Well, similar to before, we know that y is in between 0 and 10. So the minimum value this can take is 1. So here the smallest value we can have here is 61. And the maximum value we can have is 69. And That's because y can equal 9. So let's just write that down. So the current maximum working value is 69, and that's because y is in between 0 and 10. So the largest value y can take is 9, i.e. 60 plus the 9 is 69. And that is, of course, less than the minimum value we had here, which is 71. So the order of labeling for G is 6, because its current final value is 60 plus y. And if we add 60 plus y to 24, we're going to get a value bigger than 84 if we assume that we have the largest value of 69. So therefore, f has a order of labeling as 7, with us having a final value of 58 plus x. So if we think about how this helps us, remember, if we go back to the question, the shortest route from f to g via a is 140. So we need to go from f to a and then from a to g, and that total length is 140. So let's write some of this down. We are going for part B of the question, so this is part B. We're going from f to a. So from f to a, we have the length of that being, well, from a to f, that's 58 plus x, so f to a will also be 58 plus x. So here we've got 58 plus x. And then from a to g, if we go back from a to g, that's 60 plus y. And therefore, we can see that going from f to a to g, this will be 58 plus x plus 60 plus y, and we know that this is equal to 140. So this over here is equal to 140 because we were told in the question, shortest route from f to g via a is 140. Now, if we use the inspection route method, in other words, the Chinese postman, the only odd vertices will be A and G. Okay? So with the route inspection method, the odd vertices are A and G. And that is what we established over here. We found that A and G are the only vertices which are odd. And the total weight is 320 plus x plus y. So repeating AG, okay, so if we repeat AG, like so, here we need to add on the shortest from A to G, which we know is 60 plus y. Okay? So the shortest path from A to G is 60 plus y. And therefore, for the total length of the route, you'd find here we have 320 plus x plus y. Okay, so here we've got 320 plus x plus y plus another 60 plus y. In other words, the total length of the route will be over here 320 plus x plus y plus 60 plus y equals, if we go back to the question, 409. Okay, so this is equal to 409. Okay, so here we have 409. So we need to find out what x and y are. So we need to solve these two equations simultaneously. Let's call this 1 and call this 2. Okay, so if we solve those simultaneously, well, from equation 1, if we simplify equation 1, we have x plus y equals 22, and from equation 2, if we simplify this, you'd find we have x plus 2y equals 29. Now, of course, here the x's are the same, so we subtract these equations, we are left with 1y equals 7. And when y is equal to 7, we've got x plus 7 equals 22, and therefore x is equal to 15. So we have our solutions: x equals 15, y equals 7. For question number 7, a maximization linear programming problem in x, y, and z is to be solved using the two-stage simplex method. The partially completed initial tableau is shown below, that's what we see here, and for part A, using the information in the above tableau, we have to formulate the linear programming problem, state the objective, and list the constraints as inequalities. So, if we use that table, what you can see over here for part A is we have, if we take a look at the P row, we've got minus 2x, minus y, minus 3z. We've got no slack and artificial variables, and the value of this is equal to 0. So we have P minus 2x. Well, rather, here it's a maximization problem. We were told that in the question. So what we have to do then is maximize P minus 2x minus y minus 3z equals 0. In other words, we can write this as P equals 2x plus y plus 3z. We'll call this equation 1. And this maximization problem is subject to the following equations. So, if we go back to the table, take a look over here, we've got 1x, 2y, 3z, and one s1 variable. We've got one slack over here, and this is equal to 45. So here we've got x plus 2y plus 3z equals 45. I'm going to call this equation 2, and because we have to write these as inequalities, rather here we've got plus s1. This is equal to 45. Call this equation 2, and because we have to write these as inequalities, here you can see we've got x plus 2y plus 3z being less than or equal to 45. And now if we take a look at the next row, we've got 3x, 2y, 0z, 0 s1s, minus 1 s2, 0 s3s, and one A1. So here we've got 3x plus 2y, we've got 0 z's, and we have a minus s2, and then we have a positive a1, and this is equal to 9, as we see from here. So we'll call this equation 3, and because we have to write this as an inequality, we've got 3x plus 2y, and because we've got a minus slack plus an artificial, this will be a greater than or unequals to inequality. So we've got 3x plus 2y being greater or equal to 9. And then we've got minus x, 0y, and 4z, no s1, no s2, but we've got minus an s3 and plus an a2, and this is equal to 4. So if we write that down, we've got minus x plus 4z minus s3 plus a2 equals 4. So we'll call this equation 4. And if we write this as an inequality, we've got minus x plus 4z, and because we've got a minus slack plus an artificial, we've got a greater or equals to inequality. So minus x plus 4z is greater or equal to 4. For part B of the question, we have to complete the bottom row of table 1 in the answer book. It should make your method and working clear. Well, of course, what we need to do here is make a substitution, and it's a standard two-stage simplex method. So for part B, we will let A equal minus the sum of A1 plus A2. And the reason we are doing this is because minimizing A1 plus A2 is the same as maximizing minus the sum of A1 plus A2. So what we will do over here, if we move this to the right a bit, let's call this equation number 5. Okay, now what we can do first of all, if we add together equation 3 and equation 4, we will get something involving an A1 plus an A2, so we can make this substitution. So if we add together equation 3 plus equation 4, we would have, if we add those together, well here we've got 3x minus x, that's 2x. And then we've got 2y and 4z. So we add on 2y and 4z. And then we've got a minus s2, a minus s3. And then we've got a positive a1 and a positive a2. And this is equal to 9 plus 4, which is 13. And we'll call this equation number 6. And now, because here we've got a a1 plus a2, we can substitute 5 into 6. So we will substitute in equation 5 into equation 6. So here, if we do that, we've got 2x plus 2y plus 4z. Here we're going to have minus s2 minus s3, and because a1 plus a2 is equal to minus a, here we subtract off a, and this is equal to 13. We'll call this equation 7, and if we multiply equation 7 by minus 1, so we will multiply equation 7 by minus 1, you'd find here we have a minus 2x minus 2y minus 4z plus s2 plus s3 equals minus 13. we'll call this equation 8. And now what we need to do is simply substitute in 8 into table 1. So let's just write this down. See table 1. Okay. So if we substitute these in, we have here minus 2, minus 2, minus 4. And here we've got 0s1, 1s2, 1s3, and we've got 0a1 and 0a2, and this is equal to minus 13. Now, the following tableau is obtained after 2 iterations of the first stage of the 2-stage simplex method, and for the first part we have to explain how the above tableau shows that a basic feasible solution has been found for the original linear programming problem. Well, quite simply, in the given tableau, the value of the objective A is equal to 0. So if we go back, you'd find over here the value of the objective A is equal to 0. And that's exactly what we see here for this objective A. So this indicates that a feasible solution has been found. And now for the next part of part C, write down the basic feasible solution for the second stage. Well, here we've got x equaling 3. So let's just write this down. We have, for the next part of part C, x equals 3. Y is equal to 0. So we've got y equals 0. We've got z, which is equal to 7 over 4. And we've got S1 equaling 147 over 4. So here we've got S1 equals 147 over 4. S2 and S3 will also equal 0, and of course A1 and A2 are equal to 0 because the value over here is equal to 0. So S2 equals 0 and S3 equals 0. For part D of the question, taking the most negative number in the profit row to indicate the pivot column, we have to perform one complete iteration of the second stage of the 2-stage simplex method to obtain a new tableau. T. Make a method clear by stating the row operations you use. So here is where we will do part D. Now first of all, we need to identify where we'll use our pivot. So here is where our pivot will be. This is the pivot column, and our pivot will be the 7 over 12. Okay, so this here will be the pivot because when we come to work out the theta values, here we do value divided by this, the values in the pivot column, and you'd find here we get negative values. So let's just demonstrate that on our calculator. Let's just clear the screen. Here we've got 147 divided by 4 divided by 7 over 12. So you'd find here we get theta equals 63. And then here we've got 3 divided by minus 1/3, which is minus 9. And here we get 7 over 4 divided by minus 1 over 12, which is minus 21. Here we have negative values, so this is our pivot row, so this is our pivot. Now, if we call this row 1, this row 2, this row 3, and this row 4, here we're going to have row 5, row 6, row 7, and row 8. Now, ideally, we want a 1 over here. So how do we go from 7 over 12 to 1? Well, here we would have to divide row 1 by 7 over 12. So we'd have to divide row 1 by 7 over 12. Now, we want a 0 here, so how do we go from the minus 1/3 to 0? Of course, we'd have to take our second row and add on 1/3 of row 5. We want a 0 here. How do we get a 0 here? Well, we'd have to take our third row and add on 1/12 of row 5. And for row 8, how do we go from minus 11 over 12 to 0? Well, here we would have to take row 4 and add on 11 over 12 of row 5. So here are our row operations. Now, on our calculator, we can actually perform the row operations, but if not, then here you simply have to work all of these out. But it's much easier on the CG50. So from the CG50, before we do anything else, you'd notice the pivot column corresponds to S2, so the basic variable will increase to S2 from S1. And here we'd have X and Z. So from our CG50, we can click F3, and if we create a new matrix, here we've got 1, 2, 3, 4 rows, and the number of columns we've got 1, 2, 3, 4, 5, 6, 7. So now we need to type in the entries as we see. So here we've got 0, 5 over 6, 0, 1, 7 over 12, 3 over 4, and 147 over 4. Now here we've got 1, 2/3, 0, 0, minus 1/3, 0, and 3. Here we've got 0, 1 over 6. Okay. So here we're going to have 1, 0, minus 1 over 12, minus 1 over 4, and 7 over 4. And here we're going to have 0, 5 over 6, 0, 0, minus 11 over 12, minus 3 over 4, and 45 over 4. So this is our completed matrix entered into our calculator. And if we click F1 for row operations, we will multiply the first row by 12 over 7, which is equivalent to divided by 7 over 12. So here we have 12 over 7. So if we execute, here we've got 0. Here we've got 10 over 7. Here we've got 0. Here we've got 12 over 7. We've got 1. 9 over 7. And 63. We now need to apply the other row operations. So here, if we click F3, we will multiply the first row over here, which corresponds to row 5, by 1/3, and we will apply this to the second row over here. So if we execute this, here we've got 1, 8 over 7, 0, 4 over 7, 0, 3 over 7, and 24. Let's apply row operations again, so click F3. We will multiply 1 over 12 by the first row here, which corresponds to this row 5. And we will apply this to the third row here. So if we work this out, we've got 0, 2 over 7, 1, 1 over 7, 0, minus 1 over 7, and 7. We will apply row operations again, so click F3. We will multiply 11 over 12 by the first row here, which corresponds to row 5, and we will apply this to the fourth row over here. So if we work these out, we've got 0, 15 over 7, 0, 11 over 7, 0, 3 over 7, and 69. So this is the first iteration completed. For the first part of part A, we have to explain, using T, whether or not an optimal solution to the original linear programming problem has been found. Well, here, of course there's an optimal solution because there's no negative values in the objective P row. And for the next part, we have to write down the value of the objective function and state the values of the basic variables for the third part. So, for the second and the third part, well, let's do the second part first. You'd find over here P to equal 69. And then for the next part, for the basic variables, S2, that's equal to 63. So we have S2 equals 63. X is equal to 24. And Z is equal to 7. So this is the end of the paper.